Hello everybody, in this lecture I will be solving 1992 IMO problem number 3. It is a combo problem and here is a view of this problem. We're given 9 points in 3-dimensional space and no 4 of them are coplanar in the same plane. Each pair of points is joined by an edge, and those edges are then either colored blue or red, or they are left uncolored. So we have a complete graph in our disposal, and in total we have 9 points, 9 choose 2, 36 edges, and connecting all these 9 points to each other. Okay, and then we would like to find the smallest value of n such that whenever exactly n edges are colored, the set of colored edges necessarily contains a triangle, all of whose edges have the same color, and obviously either red or blue. Okay, so let's first label the 9 points as 1, 2, all the way to 9, and then I would like to find out what is the maximum number of edges that I can color and yet no single color triangle arise out of this coloring, right? So I claim that I can color in fact 32 edges and yet no single color or monochromatic triangle. So for the proof, let's color blue, an edge blue, and so we colored an edge blue if the difference of labels in endpoints of that edge, points of a given edge is either 1 or 4 or 6. Is that clear? So let's see if we can make sense of this coloring. Okay, so suppose that one of the vertices is 3. As a result, let's say that I decided to color blue, like in here, this edge, because 4 minus 3 is 1, and it's obviously here. And let's say this one is also 3 is also connected to 2, and that one is also colored as blue, and then 7 is also colored blue. All these colorings are blue. In fact, 3 to 9 is also blue. So inside the proof I would like to make the following claim. I claim that no blue triangle with this in this coloring scheme will exist. So so the blue segments will not form a triangle, and you can just consider a triangle such that so consider a triangle with 3 vertices as I, J, and K, and if all its sides were blue, then what it means is that the differences I minus J, let's just call it X, J minus K, let's just call this one as Y, and I minus K, you can just simply add up the first 2 equations to find that this would be just X plus Y. So so these differences are supposed to belong to this set 1, 4, or 6. However, this is impossible because, for instance, if X is 1, Y is 4, their sum, which is the other edge, is only 5. So there's no way that I should have colored this one as blue, right? And so on. So no 2 elements in among 1, 4, and 6. So no element is equal to the sum of the other 2 elements. So as a result, our claim holds. There does not exist any blue triangle in this situation where the difference of the endpoints is equal to 1, 4, or 6. Now we can extend this claim further we can also claim that the same thing will hold. We can color red if the difference of endpoints is 2, 3, 7, or 8. So if the difference of the endpoints is 2, 3, 7, or 8, well, again, there does not exist any element in this set which is equal to the sum of any other two elements from that set. So as a result, we won't find any red triangle from among these edges by the same reasoning and arguments. Now, so far, how many edges have we colored? So we have colored all the blue edges according to this rule, and we have colored a lot of red edges according to this rule. So the ones that are uncolored, so yet to be colored, or you can just say uncolored, are the ones which have a difference of 5, sorry. So which is 6, 1, 7, 2. So these are the endpoints, endpoints of each edge. 8, 3, and 9, 4. So we are still missing 4 edges. So as a result, the total number of edges is, as we said earlier, 36. But 4 of them are for sure not colored yet. So based on the two above claims, arguments, so namely this one and this one, if you combine these two, we will get to that big claim that we can color 36 minus 4, 36 minus 4, these remaining 4, which is equal to 32. So we can color this complete graph, 32 of its edges, and yet no single colored triangle would emerge out of this coloring. So now in the next step, I would like to show that we can not increase this number 32 any longer, and as a result, if I color in any way I want 33 edges from among those 36, then we would surely get a triangle colored, all its edges colored either blue or all its edges colored red. And so let's write our final claim. So I claim that if one colors 33 edges, then necessarily a single color triangle, either blue or red, when I say single color, will emerge. Okay, so let's consider a coloring. So we have a complete graph with 36 edges, and let's assume that so forget about the arguments so far, so up to now. So all these arguments above here were to prove that it is possible to color 32 edges. Now for 33 edges, let's assume that we somehow colored 33 edges, and there's still 3 edges left uncolored. I want to focus on these 3 edges, and I would like to color at one endpoint. So color one endpoint of each uncolored edges. Okay, so color one endpoint. So let's say that color each uncolored edges by brown. Okay, so so each one will be colored by brown. The color brown. The color brown. Well, because we have 3 uncolored edges, if the 3 edges are not connected like that, then yeah, so you would have one one endpoint colored brown. But it might as well be that some of these lines, they meet at a vertex. It doesn't matter. So if you just color this one brown, and that's perfectly fine. So there's nothing to worry about. And then all the remaining endpoints, namely so at least 6, right? So in this situation 6, but maybe in this situation 7, and so on. So at least 6 remaining vertices. So let's color them color yellow. So color the remaining at least 6 vertices as yellow. And because we have colored one endpoint of each uncolored edges by brown, so what it means is if you have 2 yellow vertices, endpoints, then the edge which will connect them will necessarily be colored, right? So it will be colored. So it will be either red or blue, right? So these edges connecting 2 yellow vertices will be colored either red or blue. So consider a yellow vertex. So we have a yellow vertex, and let's label it as L. So this yellow vertex, and we know that we have at least 5 other yellow points, right? So at least 5 other yellow points. So what I will do is I will well, because we are connecting 2 yellow vertices, so they are colored either red or blue, but because we have 5 it has to be clear that at least 3 of them, by pigeonhole principle, at least 3 of them is the same color, right? So let's say 3 of them are red and 2 of them are blue. So these 3 are colored red. And let the other endpoints be I, J, and K for those 3 red lines, right? So red edges. The other one we decided to call it as L. Now what's funny is when you consider these 3 points, obviously these 3 points are also connected amongst themselves. So like that, and like that. And because they are all these vertices are yellow colored, these connections will be colored all 3 color, right? So now I need to be really careful because because I already have 2 reds here, right? So for instance, so I can definitely not color this one as red as well, right? So I have to color this one as blue. In a similar way, I have already 2 red here, so this one is also between J and K has to be blue as well. And finally, consider between I and K. If I color it as red, I already have 2 reds here, so that would make a triangle. So I have to color also this one as blue. So what came out is that this triangle turned out to be all blue, right? Because, does that make sense? So the argument is, I think, pretty clear, right? So let me repeat the argument. So we have already these 3 red colors. Unfortunately, I did draw them with the... Maybe I should have done it like this. So these 3 are already red. So I should be careful, because if I connect I and J with red, then it means triangle LIJ is all red color. So I don't want that. So therefore, this one has to be blue. So this guy has to be blue here. In a similar way, if you consider JK, if I can color JK as red, then LJK would be all red monochromatic triangle, so I don't want that to happen, so this one has to be blue. And finally, I to K, if I color it red, then LIK will be red, so therefore I have to color it blue, but then it forced it to make the triangle IJK as blue. So therefore we had to, so we have no choice in this one, right? So you cannot avoid a single color, either a red or a blue color triangle to emerge out of this. So therefore we can conclude that when n is equal to 33, if I color 33 of the edges, then necessarily a monochromatic triangle will emerge, and that solves our problem. So this concept and this topic is deeply related to Ramsey's theorem, and for those interested, so just as a reference, so make sure to have a look into this subject, which is Ramsey theorem, which is kind of very important theorem in combinatorics, right? Okay, so hope you enjoyed this video and looking forward to see you guys in our next video.